I did this wrong. In this example, right, it's like an action potential. Okay. So in this example, when we have our measuring device and we open that channel, we're going to expect that we're going to get the 60 millivolts magnitude of the membrane potential, and it will be positive in this case because only potassium is the ion that flows. So now a couple of notes on membrane potentials. The Nernst equation gives us the magnitude of an equilibrium potential. It does not tell us how many ions are flowing to get there. How many ions are going to flow will depend on the two concentrations, and it will depend on how big the compartments are. But you can assume that it's a relatively small amount of ions in a biological context. So this is why if we shut down the sodium potassium pump in a neuron, action potentials are still possible repeatedly. Because it takes few ions to form that significant potential change. So just in this example, not a lot of sodium ions will flow. That is good to keep in mind. Now, the third note is the most important note, and it will really help you on the second exam. If you go back and you look at what we can calculate with a couple of equations that we've looked at, these are just things that physical chemistry gives us, right? And really, what we see that if we measure here 60 millivolts, you see that that 60 millivolts is really driven by a 10 to the first concentration ratio. And if we think about what it would take to establish a 10 to the first concentration ratio only, that was 1.4 kilocalories per mole that needed to be invested. So the energy stored in 1.4 kilocalorie per mole in magnitude is the same as the energy stored in a 10 to the first concentration gradient. And when we think about 300 Kelvin, 27 degrees, it is also 60 millivolts. So these three things, 60 millivolts, 10 to the first concentration ratio, and 1.4 kilocalories per mole, that's the same. It's the same, it's all energy, but it's the same package of energy. It's all currency that the cell can use. And essentially we can say that maybe you can say the membrane potential, that's kind of your credit card account, that's your bank account. And in there you can put dollars, right? And you can also invest in stocks or something like that. It's all money, currency, things with which you can do things. In terms of cellular energy, potentials, concentration ratios, and discrete amounts of energy are the same, and these are the conversions. So this is the currency conversion, if you want. So it really helps if you think in these terms, which you can quickly understand a lot of things. So I'd like you to be convinced that we can say there's a standard energy package. If we think that we're at a nice temperature and the numbers are easy, then we can say that one package of energy, 60 millivolts, is 10 to the first concentration difference, is 1.4 kilocalorie per mole. Or two packages is double of that, or three packages, on and on and on. And if the net amount of energy in kilocalorie per mole is a negative number, we're looking at an overall reaction that is favored. We can say that's credit, that's something that allows us to do work. If it's a positive number, then it is something we have to pay for, then it's a debt. And I think that really makes your life easy. Of course, we can work with things that are, let's say, 75 or 89 or whatever weird voltages, and we can also convert that to concentration ratios and amounts of kilocalorie per mole, but the numbers are not easy. So at my exams, the numbers always are in standard packages or multiple ferro. And so you don't have to remember any equations. You can't, and you can calculate everything, it will take you a lot of time. But your insight is not better, I believe. Okay, so now how can we use this? How can we use this? So we have a fungus. Let's say here we have a fungus. And it's a fungus, and the fungus is establishing a membrane potential with the aid of a pump. It's a fungus, so it's not a mammalian cell, so it's not a sodium potassium pump, it's a proton pump. Remember that? So we have a pump here, and this pump moves protons. This is a tricky part, it shouldn't be tricky, you need to remember. Okay, now that pump moves protons at the expense of ATP hydrolysis. So if ATP is hydrolyzed to ADP and inorganic phosphate, let me just say that in this cell, under the conditions that we have, under the given ATP and ADP ratios, the total amount of energy released by ATP hydrolysis is negative 11.2 kilocalories per mole. Now, if you do quick math, you see that that's 8 standard packages. Good that's 8 standard packages. Okay, so we have here a pH of 3 outside and a pH of 7 inside. pH means the negative 10 log of the proton concentration. So the change in pH here is 7 minus 3 is 4. So we have 10 to the 4 concentration difference for protons. Question to you, if we move protons out, is the movement of protons favored by the proton concentrations in the system? Yes or no? It is not. We move against proton concentration, so that's going to require energy input. Okay, so now we get the question, for this system, what is the membrane potential that this pump can establish using the parameters that I'm giving you? So we reason that the membrane potential is going to be positive outside, as always. Except for the action potential situation. That's the exception, remember? No action potential here. We're in a fungus, we're safe. So the pump moves protons to an equilibrium. At the equilibrium, the total delta G equals 0. Nada. Okay? So at that equilibrium, the energy that is released by ATP hydrolysis equals the total energy that is stored in the electrochemical gradient in terms of magnitude. So delta G is 0 at the equilibrium, all packages are then spent. I'm going to think in terms of packages, do this very quickly. So ATP negative 1.2 or 11.2 kilocalorie per mole, that's 8 packages of credit. I call it negative 8. Credit. Negative is good in this case. Credit. Okay, we have energy to spend. To create that pH difference and to make it, to maintain it, to move an extra proton out, that means you have to invest plus 4 packages because it's a 10 to the 4th concentration ratio. It's the 2 to the 4th that matters. So that's plus 4 packages. So we had negative 8 credit from ATP. We have plus 4 packages to pay to get our proton against concentration. We are left with negative 4 packages of credit in the bank that we can spend. So that means we can invest in plus 4 packages that we can pay for membrane potential. Now the package size for membrane potential was 60 millivolts. And if we have 4 times package to spend, then that means we can create a 240 millivolt membrane potential. If you practice with this, you can do it extremely quickly. And doing that at the exam means you have time for other more important stuff. There will be questions of this nature on the exam. Now, I understand that you need practice. So the tasks 3 and 4 are going to give you that practice. I think I will have task number 3 up on the web this afternoon. I will make it due somewhere in the course of the next week, and then the next task will become active, and I'll give you a due date before the exam. If you invest in the practice, it's not hard. Okay. So we've covered that topic, and we have one thing to add. This is the point where the class always sighs a little. I think we should do that. You will survive. It's not hard. Okay. How do we know about some of these things about membrane potentials? Well, there are some tricks and some interesting molecules that we can use. The interesting molecules that we like to use are called ionophores. They're small molecules, and they allow transport of ions. Ionophore means carrier of an ion. Christophoro, that means if your name is Christopher, that means you're a carrier of Christ. Phoros is carrier. Okay, so there's two kinds, channels and what we can think of as things that work like uniporters or antiporters, but they really are small peptides that kind of diffuse through the membrane. One channel-forming substance is gramicidin. It originates from bacteria, Bacillus, and it's one of those molecules that bacteria use in their ecology. Bacteria are always fighting for resources. They want to kill the competition, and what better way to kill the competition than to put out a channel that sits in the membrane of your competitors and dissipates the membrane potential of your competitors, thereby killing them. That's gramicidin. Okay? It's two peptides, and when they're aligned, they form a channel that's pretty unspecific. But there are other molecules like volinomycin. It's actually a strange peptide. It's circular. There are D and L amino acids in it. It binds potassium and it moves it across the membrane. Nigericin is a similar molecule, but it exchanges potassium for hydrogen. And that's this guy, A23187. I don't know how they came to that name. It carries calcium across membranes. And here's CCCP. This is a weak acid. Similar, ammonia is a weak acid. And weak acids are substances that can be found dissociated or not, so they either bind the proton or not. But they're not only weak acids, they're also, they delocalize the charge in the charged form, and therefore they are membrane permeable, both charged and uncharged. Why do we not pee out ammonia? Animal diets are characterized by excess of nitrogen, if you didn't know. We eat more protein than we need, typically. That means we have to get rid of nitrogen. That's an important component of amino acids. We don't pee out ammonia. Why not? Ammonia is not tolerated in the body because it moves protons across our membranes. It will dissipate our membrane potentials, which we do not want. So that's why we pee out urea, which is uncharged. It has the ammonia, but the nitrogen bound in a different way. Okay, there's another interesting molecule called TPP+. This is tetraphenylphosphonium. It is a phosphorus with around it 4 phenyl groups. It's a delocalized, actually positive charge. It doesn't carry ions across the membrane, but it wants to move itself across the membrane in response to a membrane potential. And these guys can all be used for interesting experiments. For instance, here, if we have here a small membrane vesicle formed, and let's say we form our vesicle in the presence of this concentration of potassium chloride, 100 millimolar. And then we put it in centrifuge, and we collected our vesicles with the potassium chloride still inside. And then we put on another solution which has now a lower amount of potassium chloride, and to keep everything isotonic, we have sodium chloride in there as well. So we have this vesicle, and now we throw in valinomycin. And now you remember, you need to remember valinomycin and nigericin, what it does. We throw in valinomycin, and we know it's a pathway for potassium. So we're going to predict that potassium flows out, down concentration. So what will happen to the membrane potential? A positive charge leaves, the chlorine negative charges stay behind, you get positive out, negative in. What is the magnitude of the membrane potential? Simplified Nernst equation, or say one standard energy package, 60 millivolts. Right? That's what you'll get.